Okay, yesterday we talked about metallic bonding. So today we move on to something a little more interesting. What if we have a metal and a nonmetal? So what do we know about the personalities of metals? All right, they tend to lose electrons. They are weak. And then nonmetals, well, you can guess, are strong. So yesterday's story was all about what happens when we only have weak atoms. We saw they just kind of all hang out, share their electrons. Now, what if we have strong and weak? Well, now it's the classic story of I would go with the bully and the lunch money. Can I get 2 volunteers? All right, 1, 2. Kai, would you like to be chlorine or sodium? All right, you're chlorine. Oh, my electrons did not show up nicely.
Ionic bonding occurs between two atoms when one of the atoms has sufficient strength of attraction to remove an electron from the other atom. A sodium atom has 1 valence electron, with a stable energy level below containing 8 electrons. A chlorine atom has 7 valence electrons. If the atoms collide with sufficient energy, the chlorine atom will remove the electron from the sodium. The sodium atom loses its only valence electron and becomes a positively charged sodium ion. The energy level below now provides
What this would look like in the lab.
Sodium metal is heated until it melts and just begins to burn.
So here in that spoon, you may or may not be able to see very well. In the little spoon you have sodium, which is this metallic solid. It's silvery colored. If you heat it up and put it into this big test tube filled with chlorine gas, chlorine is this greenish gas. So if you actually put them together,
then it is immersed into the yellow-green chlorine gas. The sodium begins to burn in chlorine with an intense yellow flame. It produces a white smoke of sodium chloride. We are observing the exothermic reaction of sodium metal with chlorine gas, producing the white solid sodium chloride. Afterwards, the glass spoon contains only white solid sodium chloride.
It was heated up in a spoon to start. The reason is the reaction has a certain activation energy that needs to be overcome. We'll talk about that in January. So that's ionic bonding, okay, on the visual level, but also on the atomic level. I'm going to skip through those. they're not even that funny. So what's the point here with ionic bonding? The metal loses valence electrons to the nonmetal, or the nonmetal steals valence electrons. And once that happens, you create positive and negative ions. So the metal atoms turn into positive ions. The nonmetal atoms turn into negative ions. And what happens to those two? Attraction. So that's the basic story of it. Now the thing is, once you make ions, ions are not picky. A positive ion is not going to pair up with an individual negative ion and just be satisfied with that. If there are other negative ions around, the positive ion is going to be attracted to those too. So instead of just forming individual pairs, what happens is each positive ion surrounds itself with negative ions. Each negative ion surrounds itself with positive ions. So what you end up with is what we call a crystal lattice of alternating positive and negative charges. So there's no individual bonds between ions. We'll usually not refer to ionic bonds. We'll refer to ionic bonding because there's always going to be alternating positive and negative charge in the crystal structure. And in 3 dimensions, it looks a little different. If you take an inorganic chemistry class in the future, you may spend a lot of time classifying the different kinds of structures of these crystals. We're not going to do that. The key to take away is ionic bonding is not something that happens just between 2 atoms at a time. It's always going to be a bunch of atoms that form a bunch of ions, and they stick together in a whole crystal. So this slide is just summarizing what we just said. Metal atoms are weak. Non-metal atoms are strong. So when the 2 meet, nonmetals usually steal the electrons from the metal atoms, and then the positive and negative ions will be attracted to each other, forming a solid. And we can use that simple model. Again, this model is not perfect, and it is an oversimplification. There is some degree of sharing between atoms, but we ignore it when we think of ionic bonding. This simple model can explain a lot of the properties of ionic compounds. Here are just some other pictures of what different crystal lattice structures. You can see they all look more or less the same. You've got alternating positive and negative. Their arrangement in space might be slightly different. So what I want to get into a little bit is the energy that goes along with this kind of bonding. It's a nice story, this story that metals are strong enough to steal electrons, or nonmetals are strong enough to steal electrons from metals. But it's not exactly clear whether this is going to be energetically favorable or not. So what I want to do is break it up into 3 steps. mentally. And those three steps are: first, you have the metal losing electrons. Second, you have the non-metal gaining valence electrons. And then third, you have the ions coming together. So what I want to do is think about each of these steps and whether it's going to take energy or whether it's going to release energy. So step one was the metal losing the electrons. At your table, I want you to discuss for a moment, is that going to be endothermic or exothermic? Do we have to put in energy to make that happen, or is that going to release energy when it happens? Okay, 20 seconds. All right. Rachel H., what was the discussion at your table like? This is endothermic, great explanation. Endothermic, because the electrons are attracted to the nucleus. So separating them requires an input of energy. In other words, potential energy increases. And we actually have a name for this. How much energy does it take to pull an electron away from something? Ionization energy. All right, so we call this ionization energy. All right. So then, how about the second step? The second step we said would be the nonmetal gaining an electron. I want you to talk for a moment whether you think that's endothermic or exothermic. All right, Katie, what did you guys decide? It's exothermic. It does give off energy. Electrons are attracted to atoms, even in a neutral atom. There are certain neutral atoms that electrons won't be attracted to, particularly ones where it would have to go into a higher energy level. So ones that have a filled energy level, you try and add an electron to them, it's going to a higher energy level, and Z effective would be 0. So electrons don't want to be added to those. But for most atoms, it's exothermic because the electron is attracted to the atom. As long as it doesn't have 0 Z effective. And so bringing them together releases energy. Question? All right, so Z effective is the effective nuclear charge. Remember, you have a positive charge in the center of the atom at the nucleus. And then you've got some inner electrons, and then you've got electrons further out. Z effective is, for this further out electron, what's the charge that it actually feels from the nucleus? So this looks toward the nucleus, and let's say there's 3 positives. Say this is lithium. There's 3 positives in the nucleus. It looks in that direction, and there's 2 negative charges kind of screening its view of the nucleus. So really the only thing it feels is 1 positive charge. Okay? So that's what Z effective is. Now, if you looked at, say, helium, and you were to try to add an electron to helium, how many protons are in the nucleus of helium? There's 2 protons in the nucleus of helium, and then 2 electrons. If you add another electron to that outer layer, to energy level 2, it'll say, no thank you, because it can't even see the positive charge in the nucleus, because it's completely screened. So the question is, can you say this is because it's being repelled by the inner electrons at the same time that it's being attracted by the nucleus? And the answer is yes. That's exactly what shielding is the repulsion from the electrons essentially cancels out the attraction from some of the protons. So this is an exothermic process. We call this the electron affinity. We call that the electron affinity of the atom. So it's the energy released when an atom gains an electron. It's called the electron affinity. So we can actually look up these numbers. We can look up electron affinities, and we can look up ionization energies and compare them. So what I want to do is take, what would be as ionic a case as you could possibly think of. What's a super, super weak atom? Cesium, way bottom left of the periodic table. So cesium is about as weak an atom as you're going to find. And then what what is a really, really strong atom? Fluorine. All right, that's as strong a nonmetal as you're going to find. So let's look up the values of these two things for cesium and fluorine and see what we find. How would I find the ionization energy of cesium? The internet, which is magic. I agree. All right, cesium, I want... there is some chatter in the room about the spelling of cesium. This is a British website. They're using the British spelling. So this tells me the ionization energy for cesium is 375.7 kilojoules per mole. The other thing I wanted to know was, for fluorine, what is its electron affinity? So you're going to give me electron affinity. Electron affinity is 328 kilojoules per mole. Okay, so we chose the weakest element we could think of, which was cesium. And in the example of cesium, the ionization energy was, we'll call it 376 kilojoules per mole. So we've got to put in 376 kilojoules per mole to remove electrons from cesium. Then we looked up the electron affinity of fluorine. And the electron affinity of fluorine was 328 kilojoules per mole. So as an example, okay. So what that means is fluorine, when it takes an electron, releases 328 kilojoules per mole of energy. So let's go back to our story here. Our story was the nonmetal really wants to gain electrons, and so the nonmetal steals the valence electrons from the metal because the nonmetal's stronger. To take the electron away, we have to put in 376 kilojoules per mole, and then when the electron's added to fluorine, we get back 328 kilojoules per mole. Is that process, just with those first two steps, favorable? No, because we're putting in 376, we're getting out 328. So we actually have to put in 50, almost 50 kilojoules per mole to make that process happen. And that's the best case scenario. That was the weakest element with the strongest element. So, what's a really important part of ionic bonding? Not magic. Step 3. Step 3, we said, is when the ions come together. All right, when the ions come together to form a crystal, now we're taking positive charges and negative charges, and we're saying, hey guys, get together. In terms of energy, is that going to be favorable or unfavorable? I don't think there's necessarily a need for discussion here. Sam? Yes, favorable or unfavorable? All right, thank you, Sam. It's going to be favorable, very favorable. It's going to be exothermic because you're bringing positives and negatives, things that are attracted to each other, together. So the reason I belabor this point a little bit is because there is a common misconception after first year chemistry courses. Now, common misconception, we chemistry teachers feed a little bit because we use an oversimplification. We usually talk about what we call the octet rule, that atoms tend to, in stable compounds, end up with 8 valence electrons. But we allow that statement sometimes to get morphed into atoms want to have 8 valence electrons. So students sometimes think cesium wants to lose an electron. Does cesium want to lose an electron? No. You have to put in 376 kilojoules of energy to remove electrons from a mole of cesium atoms. Cesium does not want to lose an electron. Does fluorine want to gain one? Absolutely. Fluorine definitely wants to gain one. So that part is true. But the key that makes the bonding work is not that cesium wants to lose and fluorine wants to gain. It's that fluorine wants to gain. Cesium is pretty weak. And then if you take electrons away from cesium and give them to fluorine and then allow those ions to come together, the net process as a whole is going to release energy. So this amount of energy is known as the lattice energy. And if we look at the whole three-step process, the ionization energy plus the electron affinity and the lattice energy, when we put those three things all together, that's what makes ionic bonding favorable. So this is also a number we could look up. I'm not gonna look it up right now, just in the interest of time. But if we looked it up for cesium fluoride, it would be some huge number that would dwarf the 50 kilojoules per mole that we had to put in to make the first two steps happen. And so the net result is that we get an energetically favorable process, which we saw in the formation of sodium chloride. What in that video, when sodium chloride was being formed, told us that energy was being released? Flames. So we saw light, presumably heat. So that's a sign, all right, this is an energetically favorable reaction. It's releasing energy. So the question is, for fluorine, this 328 kilojoules per mole, is that a small number compared to other nonmetals? And the answer is, no, that's actually a big number. There's only one that's actually bigger, and the reason that it's bigger is kind of complicated, and I don't want to go into it. But chlorine's the only element that has a bigger electron affinity, and I think it's maybe 350 or something like that. So this is about as big as electron affinities get. So the point is, I don't want you to have this idea that metal atoms want to lose their electrons. It's just that they're not strong enough in the face of these other two steps. The metal is not strong enough to hold on to its electrons. That's why I made the analogy earlier to the bully and the lunch money. It's not that the little kid in the TV show wants to lose his lunch money. It's just that not strong enough to keep it away from the bully. The other misconception is that, well, nonmetals want to get up to 8 valence electrons, and that's not even true. So if you looked at any example with oxygen, oxygen wants to gain 1 electron. Its first electron affinity, it would release energy. But actually, to give oxygen a second electron is energetically unfavorable. If you think about it, for fluorine or for oxygen, electron affinity is going to be some number. I'm not going to look it up. But if you tried to add a second electron, if you thought about the electron affinity of O minus, think about it for a second. You have O minus and you have an electron. What are those two things going to do when they see each other? They're going to repel. So even oxygen wouldn't accept a second electron if you tried to give it to oxygen alone. We will see ionic compounds where oxygen does take 2 electrons. How is it that we can convince oxygen to take that second electron? Lattice energy. Because when you combine all the steps, the metal losing the electrons, oxygen gaining 2 electrons, and then putting the ions together, the overall result is a favorable reaction. So the lattice energy becomes important in making ionic compounds favorable. So for oxygen, electron affinity would be some number. For O minus, there is no electron affinity because it doesn't want to accept a second electron. It's not going to release energy if you give it a second electron. So we have this 3-step process. We had step 1, unfavorable. Step 2, energy comes out, maybe a little bit. And then step 3, the lattice energy, that's usually a huge number, and that's what drives the reaction. That's what makes it favorable. So we have one unfavorable step, 2 favorable steps. And we need the 2 favorable steps to outweigh the unfavorable one. So you're all probably familiar with the octet rule. Yeah. All right, so favorable. Reactions are favorable when they release energy. They're unfavorable when you have to put in energy to make them happen. Yeah, good question. So how can I state the octet rule in a way that's not necessarily building a misconception? I try to be careful in the way I state it. The way I state it is that in stable ionic compounds, each ion tends to have 8 valence electrons. And if I want to explain that, if I want to explain why there is this octet rule, a lot of it comes from the metals perspective. Oh, let's see, do I want to? Yeah, a lot of it comes from the metals perspective. So if I go back to cesium, and I go back and look at its ionization energy again, it has one valence electron. So that first valence electron doesn't take a lot of energy to take away. 376 is a pretty low number. But if I go back to cesium and look at, well, what if I were to take a second electron away? How does the second number compare to the first? It's much bigger. We go from 380 to 2200. So that's like a 5-6-fold difference. Why is that? All right. The answer that Bill gave was because you're taking an electron out of a filled valence shell, but I want to change your answer. I'm glad you gave it because, again, I'm not quite satisfied with that language. Why is it that it takes so much more energy to pull the second electron out? Okay, it's partly because after you've pulled one electron out, the second electron is now more attracted to the nucleus than it was before, because there's less general repulsion between electrons, so the overall attraction is stronger. But there's another important factor. The next electron is one energy level lower than the valence electron was. So now that second electron that we would try to pull out of cesium has much less shielding. The effective nuclear charge for that electron is much, much higher because it's in a lower energy level. So I wouldn't say it's because that lower energy level was filled. That does happen to be the case, and that's a good rule of thumb for us to use. But it's not because it's filled that it's harder to remove that electron. It's because that electron is in a lower energy level, closer to the nucleus than the valence electron was, fewer electrons between it and the nucleus. And so we'll see that anytime we go from the valence energy level to the next level below, there's a big jump in ionization energy. So if I take, for instance, calcium, which has 2 valence electrons, and I look at its first ionization energy, is about 600 kilojoules per mole. Notice that's much higher because calcium is in a lower is higher in the periodic table. Its valence electrons are a lot closer to the nucleus than cesium's. But its first ionization energy is 600. Second one is 1200 or 1100 something. But then again we go to the third electron and it takes 5 times as much energy to remove that one. So those first 2 ionization energies are small enough that they can be overcome by the lattice energy. And so forming a calcium 2+ ion and then making a calcium a compound out of it can be favorable overall because you can overcome those first 2 ionization energies. But that third one now is so huge, 5,000 kilojoules per mole, the lattice energy can't overcome it. So that's why calcium is going to lose 2 electrons when it forms compounds. It's not that it wants to lose 2, it's just that's how many you can get away with taking when you factor in the other steps. So the question is, are the values we're looking at, are those experimentally determined? Or are they just calculated from theory? Those are actually experimentally determined values. So I don't know the particular technique. A lot of these are measured by vaporizing the element and hitting it with light and seeing which energies of light will actually make electrons jump out. But I don't know the particulars of how they're experimentally determined, but they are experimental. And they match our theory. Our theory says that when you go to a lower energy level, it should get a lot harder to pull an electron out, and it does. So the idea here is the metal metal ionization energy is relatively low for the valence electrons only. So if you try to make an ionic compound where you remove electrons from lower energy levels, that ionization energy is too much to overcome with those other two steps. Actually, I'm going to rephrase this. So you won't observe ionic compounds where you remove more than just the valence electrons from the metal. Similarly, for the nonmetal, adding electrons to a higher energy level becomes very energetically unfavorable. So you'll never see a nonmetal where you've added electrons past the valence energy level. You generally add electrons until it has a full valence energy level, and then you stop because it becomes too costly. It costs too much energy to keep adding electrons. So this octet rule is a little more, the whole point of this discussion is that the octet rule is a little more complicated than we let on in your first year of chemistry. It's still a great rule of thumb, but I do want to break you of the habit of saying, you know, oxygen wants to gain 2 electrons, or the habit of saying sodium wants to lose 1 electron. That's not a want to. That's what tends to happen. But those things wouldn't happen on their own. It's the whole process of bonding that makes it favorable. Questions about octet rule?